Good evening, everyone. I'm Hussain Kuraudwala, Research Associate at the Good Food Institute, India. Welcome to our masterclass on protein processing hosted by GFIdeas India in collaboration with global experts from Pall Corporation and in association with our network partners, India Pulses and Grains Association and USA Dry Pea and Lentil Council. So we have today with us Stephanie Joseph. Stephanie started her career with Paul in 1994. Over 3 decades, she has really held several responsibilities in the food and beverage segment, including roles such as system sales specialist, account manager, and channel manager across different F&B applications. In a recent role, Stephanie operated as the sales director in Western Europe with a strong focus on protein ingredients. She's now heading Paul's protein segment globally, covering plant protein as well as alternative protein segments such as precision fermentation and cellular agriculture. We have also with us Rodrigo Villas, manager F&B Global Strategic Projects. Rodrigo has 20 plus years of experience in the food processing industry. He has spent the last decade focused on micro and ultrafiltration projects with ceramics and hollow fibers for the wine, beer, plant proteins, enzymes, dairy, and fermentation broth markets. Tejendra Nehete, who's the business development manager for protein at APAC, at Paul. Tejendra is right now part of the global strategic growth team. His expertise lies in identifying and implementing micro and ultrafiltration projects with ceramics and hollow fiber applications across diverse industries such as proteins, enzymes, wines, and spirits, and many more. Tejendra has about 12 plus years of experience in the filtration industry, and in his previous roles, he's worked with renowned brands and major biopharmaceutical companies. Lastly, we have with us Prashant Nadagoudar, F&B manager. Prashant is currently involved in process development and application support for the development of from pilot to plant scale optimizations across diverse food and beverage applications, including alternative proteins. He's a frequent speaker at industry events on the topics of process and cost optimization, plant scale audits, new technology adaptations, aseptic filtration, microbial stabilities, and sterility and integrity testing. The agenda for today is that I'll first go over insights about the Indian smart protein ecosystem and needs of the sector. Stephanie will then go over Paul's entry into the alternative protein sector, global trends in the sector, and work in India. And Tejendra will talk about further opportunities and challenges presented to alternative protein manufacturers in India. Lastly, Prashant and Rodrigo will talk about the science behind protein processing. So for those not familiar with our organization, the Good Food Institute India is a part of a network of independent nonprofit agencies operating in 6 key regions of the world. Put simply, we work with scientists, entrepreneurs, investors, policymakers, and other stakeholders to speed up innovation and diversifying protein sources for a more secure, sustainable, and just food system. I will talk about the Indian market and our plans for 2023 and beyond. A key question that drives our work is how we will feed 10 billion people by 2050 through systems that are sustainable, efficient, and safe. The inefficiency of animal protein production contributes to food insecurity by putting pressure on our limited land and agricultural resources. Bypassing the animal and processing more plant proteins like pulses into foods for human consumption is one of the top ways we'll be able to provide high quality protein to a fast growing and a highly vulnerable global population. Developing countries like India will be the major hotspot for this growing demand in meat consumption over the next few decades. A lot of this demand will be driven by factors such as upward mobility, rising incomes, and changing demographics. This requires food systems to be resilient, environmentally stable, and safe. The diversification of the protein supply chain has implications across different challenges facing India. High prevalence rates combined with large population means that India bears the single largest burden for child as well as maternal undernutrition worldwide and protein deficiency. On the other hand, the livestock industry is also vulnerable to endemic and re-emerging infectious diseases that causes supply chain vulnerabilities for livestock farmers. As an example, while the pandemic raged across the country, there were significant, the state of Assam was gripped under the threat of African swine fever, resulting in a culling of a large population of the farmers' livestock. So we believe that one of the key ways of solve these interconnected problems is through smart protein. Smart proteins are essentially food products that can reliably and predictably substitute the consumption of animal-derived meat, eggs, and dairy, because they perfectly replicate the sensory as well as cultural experience for consumers and offer several advantages for consumers and producers on the environmental and health metrics, so that it's a simple switch and not a sacrifice for meat eaters. Over the last 2 years, the market in India has grown to include 400 plus products, and across 35 formats and 60 plus brands across meat, eggs, and dairy, available in various channels across 19 plus Indian cities. Additionally, there are 100 plus supporting companies within the larger ecosystem who are all part of the broader B2B landscape of plant-based foods in India. There's been a significant category awareness with celebrities like MS Dhoni, Neeraj Chopra, Virat Kohli backing and investing top brands and coming on as brand ambassadors. You can buy plant-based meat and dairy products with the help of a few taps on your phone on quick commerce platforms like Swiggy, Instamart, Dunzo, and Blinkit. So what is actually the potential of this sector in India? Investors and other stakeholders have frequently asked us this question. And to answer some of these questions, GFI India and Deloitte India conducted a rigorous market study and modeling to investigate the potential for smart protein for India's economic future in terms of market size, export potential, economic impact, job creation, and more. We modeled the market size, export potential, and job creation numbers across three scenarios: low growth, medium growth, and high growth. Smart protein could be worth more than $4 billion by 2030 with the right interventions, and create up to around 4.2 lakh jobs. To be clear, these are just projections and not a guarantee. There's a lot of work to be done, including different levels of supply chain localization and investments in R&D and local talent development. To continue this momentum that we are seeing, though, in the sector, there's a need for localization of key ingredients such as protein concentrates and isolates and TVPs used to make these products, and bring the cost basis down, as it will enable greater repeat purchase. For this, there is a need for developing processing and texturization infrastructure at the lab, pilot, and commercial scales, and also need for filling in knowledge and technical gaps, and to create and operate such infrastructure and enable utilization of our indigenous crops, such as pulses and other raw materials needed for the key ingredients. So for this, we really need to set guidelines for cooperation of industry, academia, and government to unlock investment in the sector, promote research and technology commercialization, talent development, and training for this industry of the future, and scaling support to startups and businesses wanting to enter this area and lend their expertise. And this is one of our one such initiative of ours to really, bring to our GFIdeas India community some of the experts from Pall Corporation. So now, without further delay, I'd like to hand it over to Stephanie to give an overview of Pall's global work in the alternative protein sector. Thank you.
Good evening, everyone. Thank you for this invitation to present. So, do you see my screen?
Yes, Stephanie.
Okay, super. Thank you. So I'm Stephanie Joseph, so director for this new segment dedicated to protein. I've been working with Pall since 1994, and this segment does exist with Pall since last year, 1st of July. Working for Pall Food and Beverage business unit means covering all those different segments, traditional market, as you see on the screen. And now, since more than 40 years, we were working on protein with milk fractionation in dairy. So this experience drove us to enter naturally in alternative protein now. And the emerging segments we will address in this new department will be plant-based protein, precision fermentation, and cultivated meat. We will defend a sustainable approach with systems, automatic systems with no consumables, and with new interfaces like IoT, means Internet of Things, to serve digital transformation. We do offer complete process solutions such as cross-flow systems for separation, concentration, purification, but also dead-end filters for microbial control. The plant-based proteins can be sourced through several methods. Here we will have from grains and oilseeds, typically a pure extraction. We can recover proteins as well from side streams. What we used to do, it's like the different success stories we have already, recovering spent grains in breweries. So it's solid side streams. We have as well some experience in potato juice, for example, to recover protein out of it to produce a functional protein, or via fermentation process with precision fermentation. And here you see in all those process flow, we will offer a unique cross-flow solution with this ceramic membrane and extended capabilities with ultrafiltration, chromo, nanofiltration, potential reverse osmosis as well. Our experience here in downstream processing is first plant for fermentation broth clarification in 1983. We have more than 20,000 square meters of Membralox membranes installed in food. We have more than 300 systems globally. We have, as I told you, a process knowledge for more than 40 years, starting with milk fractionation, and 10 years now with protein recovery. And we have our unique solution for protein transmission with our GP ceramic membrane. GP stands for gradient permeability, and it is a product manufactured by us in France, in south of France. Those different success stories we had in upcycling, so once again, recovering from side stream product in the existing food process, like with AB InBev, the Evergrain product, EverPro, which is coming from spent grains. It's a protein-rich barley isolate. And we have on the right side here, the functional protein produced out of potatoes, and it is pure side stream recoveries. This side stream was used to feed animals, and now it's an ingredient with a very high value. The drivers with the success stories were the transmission, of course, the yield, the protein quality we got out of this process, the price per, of course, value of protein. With this unique solution, the GP Membralox membrane, which will be described with Rodrigo later on. And yes, it's the really key differentiation here is the high transmission for the first step of the process. We will help our customers as well to recycle. So this is all about side streams product or recycling CIP recovery, like recycling CIP solutions, or water recovery. So to try to be self-sufficient and to really optimize all the water consumption and energy consumption, etc. So we can help as well here with solutions. And Tejendra will describe it now. Now I hand out to you, Tejendra. It's your turn.
Yep. Thank you, Stephanie. So
there is a lot of wind. I'm sorry.
please confirm if you can see my screen completely.
Yeah, we can see your screen.
Thank you. So I am Tejendra. So I basically take care of business development activities in proteins, specifically focusing on APAC, Asia Pacific market. So I'll talk about more of like opportunities and challenges faced by the alternative protein manufacturers in India. Starting up with the protein evolution. So all we know that we were manufacturing the proteins and with the source of like wheat, dairy, and soy. The challenges come in between like pea and then the new product what we have currently manufacturing from protein from chickpea, fava beans. There are different types of beans and the other source like insects. uh, More importantly the future. We have seen that the future in terms of algae is bacteria and importantly cultivated meat. So the coming to the opportunities in India, as we all know that India is the biggest manufacturers in terms of pulses and grains. So we test with the opportunity to manufacture the proteins out of these sources. So I've listed down some examples from where we can um, get the proteins from these particular sources. Chickpea, mung bean, cluster beans are the very good source of proteins, adding to the lentils and rice. And these are the main focus area where now manufacturers are starting towards focusing on these kind of sources. Apart from, as I said, emerging market is in the algae as well as the insects.
Tejendra, you don't move your slides, right?
I'm moving.
We don't see it. If maybe I'm the only one, but does the
Yeah,
other one?
the slides are not moving.
The
Now,
slides are not moving, no.
I think we are able to see your background presentation, not the one which you are presenting.
Prashant, do you mean that you see the different slides?
let me share again, try to share
Please,
again.
yeah,
I'm
yeah,
sorry for
please.
that.
I didn't see them moving, right?
Yes, it was not.
It was not, yes.
Now,
Yeah, now it's okay.
Yep,
it's
good
it's
to go.
it's
Yeah.
moving.
Yes, yes, good
Now
to go.
it's okay.
Okay.
Yeah.
Thank you so much. Thank you so much letting me know, and sorry for the mess. Yeah. So coming to the main thing, I think where people are struggling a lot, extraction of proteins. As Stephanie rightly said that the step extraction is much important. So which can be sourced from the like grains as well as green biomass. So in grains basically which talks about if you have a flour, then we apply the defatting technique, and then a lot of conventional processes available, precipitation, solubilization, and the clarification and concentration and drying and a lot of stuffs. So I'll talk about more in the upcoming slide. Other technique is upcycling, which is in future it is much important. The upcycling by the solid streams, and the second one is liquid stream, in which we have the success story in the beer spent grain and potato starch juice specifically. First one is from the extraction from the grains. So here if we see the traditional process where crushing in place and then defatting the grains, we do have a lot of processes in between that, like precipitation, solubilization, and the centrifugation. Lot of energy losses, lot of consumable, lot of energy consumptions was there. And again we need to go with the like purification and isolates and drying processes, whereas we offer this cross flow technology, which can replace this specifically centrifugation process, save the energy, and a lot of different stuffs. In terms of green biomass, I think green biomass can be extracted by the several processes like tissue disruptions, then protein solubilization or fractionation, uh, protein precipitation, purification, and concentration. If you see over here, then in leaves specifically, we don't have much scope to do this. There are some traditional processes still going on. But if we talk about microalgae and the seaweed, then we do have the alternative technology available, and we need to really utilize the that particular thing to minimize our energy losses and maybe the maximize the protein yield as well as the efficient system. So importantly, challenges which are faced by the protein manufacturers in India. So I'll talk about first importantly raw material. Although we are the biggest manufacturers of pulses and grains and other stuffs, but a lot of raw material goes export with the different sources, and we are not utilizing that. So here I think the raw material challenge is most important thing, uh, which relates to the price parity as well. So of course, if you do have raw material unavailable, then price will get increased, which adds to the our infrastructure. Infrastructure is specific thing I think which should really need to improve in this particular market, and with the helping hands with the other technological partners as well. I will more talk about one-stop solution, because nowadays, not in this market, but other market which we are supplying, like in brewery and wine and spirit, where people are moving towards the one-stop solution, and we have seen the same trend in this particular market as well. So people are more interested in terms of one-stop solution, and definitely Paul would be the contributor with kind of technologies, with kind of several partnerships globally available. The main other things is like complexity and cost. Whatever the challenges we have seen right now, so most related to the complexity. So it's a complex structure. Even though protein is complex in terms of manufacturing, we all know that. So with this kind of challenge, we are seeing a lot of complexity, and of course the cost is getting much higher in that manner. So we will see how we can contribute in terms of complexity and cost and other challenges. So if we see protein recovery process, so conventional processes involve the lot of steps. There are total 5 steps which we have identified, and with the alternative process with the membrane technology, we can really replace the few processes. This is not a actual objective to replace the process, but if you see the target is to substitute the centrifuge, reduce the energy consumption, and of course the chemical uses. Chemical uses is something like most important in protein sector, because we all required protein should be in more in as much as in natural shape, rather than we put chemicals in between that and then we recover the proteins. The important factor is increase the yield and efficiency. So with the microfiltration process steps and microfiltration technology, it helps the improve the protein transmission, and definitely in terms of efficiency. Rodrigo will talk about the our gradient pore ceramic membrane technology more in detail, so that you will get more having understanding on it. And the last one is basically talks about the functional protein, or we can say the rich protein isolate. So as I say, means in second point, we have seen that increasing the yield as well as the efficiency. So it which importantly talks about the functional proteins and rich isolates, where people require return increase the return of investment, and I think this is where Paul can contribute. If you have the lower return of investment, then I think it contributes to lower down the complexity and the cost overall. So last but importantly, the focus is always there to reduce the waste, whether it is protein market or some other markets. We are always there to reduce the waste, and important to reduce the water consumption. As not only in Indian, but it's a global right now a key goal. to reduce the water consumption. And with the Pall membrane technology, we have several other stuffs available where we can utilize your water, and definitely we can generate high clean water yield than the conventional water treatments. With this membrane technology, it also reduces the 70% consumption of regular water with the as compared to the conventional processes. And importantly, if we have the extended product life, ceramic talks about the high mechanical strength, high mechanical resistance. So it required a lot of resistance in between that, and it runs almost like many years we have seen historically. So it also help us to reduce the waste. Last importantly, CIP solution recovery. So we do have the kind of systems where we can recover the CIP solutions, and we can really say that towards the zero water factories would be possible in future. So that's it from my side. I will hand it over to Rodrigo and Prashant to talk about more in our in terms of our technological things and other things.
Thank you, Tejendra. Can you confirm you can see my screen and audio is clear?
Yeah.
I'll just minimize this.
Yeah, we can see your screen.
Thanks, Hussain, for confirming. Thanks, Tejendra, for wonderful insight on the what Pall can do in different ways of sustainable protein production process and how Pall can definitely support. Let's talk about more how making ingredients processing more sustainable. I'll share this presentation with Rodrigo, where we'll try to give what Pall is about and how Pall can help you globally if you are planning to produce plant-based or alternate proteins. So Pall basically a provider of filtration and separation sciences, enabling technologies. With its deep customer application knowledge, we align with the customer in terms of starting from the innovation to the product in the market in terms of various steps to R&D to the piloting to the production scale. And we say the same knowledge across the globe in 110 countries where Pall can share its wing to the new startups as well as the customers who are existing in the business. Unmatched engineering capabilities, as we can clearly work with R&D to the production scale. We have the capability across the globe where we can involve our application engineers, technical specialists, as well as product management team to build a system which is as much as big as possible with 100 meter cubes up to installations and all the technologies, latest technologies involved in it. As I mentioned, we can be to a global supporter for you if you are planning and expanding it to different regions across the globe. And all the support can be leveraged from the local technical support, sales support, engineering support, where you can find many of the Pall associates located in your region as well as nearby. Delivering the most innovative process solutions, wherein, as we mentioned, Pall is always innovative in his filtration and separation solutions, providing the most valuable and innovative process solutions. With that, let us understand what the Pall process filtration and separation solutions are basically. In particularly looking into Pall Food and Beverage provides following supports. One is on the direct flow filtrations. In that, it is basically of course filtrations, fine filtrations, or a bioburden reduction or a sterilizing efficiency products in terms of carbon dioxide, CO2, or any liquid filtrations which you might need a microbial reduction as well as the clarification for your end products. and also metallic as well as the polymeric based cellulose and polymeric based depth meter sheet, the depth filter sheets and modules. Basically, these are widely used for clarifying products where you want to separate out or some of the particles in your final product. Want to more purify the protein products in the final before packaging with kind of a pre-clarification or treatment might be required. Along with that process product, we also support customers in terms of air, gas, and steam applications where you need a critical step of operations, including the filters along with the system engineering solutions. As we're talking about proteins, which we also have a solutions, as we mentioned about micro and ultrafiltration, where in the these products can help customer to overcome the fermentation clarifications, as well as the products which can help you out to concentrate the proteins which are even smaller, like 5 to 10 kDs in the range, which are scalable solutions. All of these products are scalable from anywhere between 1,000 liters to more than 100 meter cube of volumes. Along with the products, we also provide a deep solutions for the water purification systems like UF and clarifications, absorption media. Specifically, if you have a product and you want to reduce the color, taste, flavor of the product at a final stage, kind of polishing applications, we do have a carbon impregnated filter modules wherein it helps to customer to overcome challenges with respect to taste and odor. Filtration monitoring tools, which basically are the help customer to understand the limit the microbial at the final production or the final meet the QC of the final product. And also supports the coalizers and separators when you have liquid and oil pages or different challenges with respect to final products. With that, going back into the protein, the challenges, what we wanted to understand or we have experience in dealing with this alternate proteins is basically production, plant-based protein production process must preserve the natural functionalities or the properties which meet the consumer's expectations while maintaining its important role as a role regarding the sustainability goal. And today we will talk more on exploring these opportunities, understanding the protein properties and how Pall can support in terms of overcoming these challenges, basically in current state of production of plant-based proteins, as well as the potential process optimizations to ensure higher quality and sustainable products. Also talk about the solutions available to support your plant-based protein productions. We will discuss more on the micro and ultrafiltration product, and also optimizing your various product processes in terms of minimizing the components being used in the production and achieve the highest possible purity as well as the concentration of your product. So plant-based protein solutions, basically sources. When we talk about sources, there are several methods of obtaining this materials or choosing the materials. This could be either from a grains or oil seeds. This can be a mainstream, or maybe it's a byproduct from your existing process. It can be directly obtaining its flour and defatting it, and that will be the raw product directly currently being sent into the livestock that can be utilized as a source of protein. This applies basically to the grains and oil seeds, which currently being used only for the oils and fat extraction. Basically, processing side stream may be either it may be a solid stream. For example, the spent grains, which is a byproduct for beer manufacturers, which is largely sent with unused. So those can be used for the extraction of proteins, which Stephanie has demonstrated in her presentations, wherein also we can work on the liquid side streams, as I mentioned, if your product is coming from the liquid, which is byproduct of your production, maybe the potato processing unit, wherein you have different processes like chips or any other products are the main products, but the water or the liquid stream which is being used in the production has a protein. And if you want to bring some value-added product from those mainstreams, also can be processed. So basically, from our side, we divide this into solid and liquid streams, and your product also can be an alternate protein which is produced from the fermentation process, maybe single cell therapy or clonal, if you use monoclonal cell therapies to produce this. And also if you have a specific target of yeast bacteria, or has its wide experience and deep knowledge in understanding this various microbiological fermentations, different fermentation stages, as well as the processing of the post-fermentation till the you get the highest concentration of product concentrated in the filtration. With saying that, I would hand over and request Rodrigo to take over and give his deep knowledge and share the presentation with the larger team here on the expertise.
Okay, just a second. Share screen. Oh. Okay, just a second. Okay. Can you see my screen? I believe yes. So good afternoon, everyone. Good evening. So talking a little bit about the processes, the typical processes for producing proteins. The most common would be the first starting from the flowers that are produced from the extraction of edible oils, or for producing soybean meal, or after you are producing the flowers of chickpeas, for example. So you typically have the raw material, which is the flour. You go for a solubilization process where you are mixing that solid, that powder that is rich with proteins and also starches and sugars and other materials. So you start to do this solubilization in a water-based solution. Typically need this solubilization needs pH increase to enable the protein solubilization, or even some enzymes to help to release the proteins from that flour. After that, you go for a separation clarification processes, typically with decanters or disc stack centrifuges, to clarify that solution, removing the starch and all the other suspended solids. The heavy phase goes as fibers and insoluble materials, which are not the proteins. After that, you do isoelectric precipitation, where you decrease the pH or adjust the pH to the point where those proteins are precipitating. This is typically based also by adjusting the pH with chemicals. And the only point is that this can create changes on the functionality of the proteins, but is the traditional method for several proteins, especially soybean protein isolates, as for today. So after that, you go for a separation clarification processes, where you are retaining the solid part or the heavy phase of the centrifuges. Typically, you need to do some cream washing, so you wash out these proteins that are in the solid phase with more water to remove the sugars and ashes from that protein material. On these processes, you have a lot of potential losses on the liquid phases, as the proteins are in the solid side. And also this liquid phase that today is a waste, which still have a lot of proteins, creates also an impact for the wastewater production, because those proteins, as well as the sugars and the other materials that you have there, they are going to create a load to the wastewater treatment capacity. And typically this cream washing may require several steps, so a lot of water to wash out that. And every step that you are passing through a centrifuge do this cream washing, you tend to lose a little bit proteins that can be soluble in the product. And after the purification of the proteins, typically the most common is going to an evaporation process and a drying, so you can produce your protein in a pound form to be used as a food ingredient, to be mixed to ready to drink beverages, or to do as a protein a product to be a protein concentrate that's going to be used by end customers. Okay, so about these liquid side streams that we mentioned, that we tend to have some losses of the target product, especially the globulins, which are the smaller proteins. One potential usage and additional recovery that we can have using membranes especially is the ultrafiltration of that liquid phase, or even the microfiltration and ultrafiltration of that liquid phase, where on these processes you can recover the protein, wash out the sugars, and increase your yield of the product, because while you are doing the ultrafiltration, you are retaining those proteins that you are losing to the wastewater treatment. And retaining that, you can concentrate those proteins and send that back to the concentration, even as mixing of the product, or even as a completely new product. And this is a way for you to create value from the waste that you can have from a traditional process of proteins. Here we have some examples and data from microfiltration processes that we did with pea proteins in a lab scale. We tested this using several microfiltration membranes for a pre-clarification of that product. We did that with membranes from 100 nanometers, 0.2 micron, 0.8 microns, and 1.4 micron. Basically, we operated all at the same transmembrane pressure, and we saw that the 1.4 was the best one. And we redid a test with the 1.4 at a higher pressure, where we could see that even to high recoveries or concentration factors of 10 of the insoluble material, we could reach fluxes as high as 200 LMH. From a protein transmission, which is the intent that you have in this step of the microfiltration, where you are retaining the insoluble material, so fibers, starch, and other products that are not protein, and you want the proteins to pass through the membrane. We see also that the best conditions that we achieved for the transmission of those proteins were with the 1.4 and 0.8 micromembranes. So basically, 100% of the proteins that we had in that liquid stream that was going to the drain, passing those through the microfiltration to recover the permeate, we passed 100% of the proteins through that. And one important factor is that by doing that, we reduced the contamination of that material. As during the typical, the traditional way of producing proteins, you are using centrifuges and you are doing the processes with adjusting the pH and reprecipitating the proteins. That liquid streams had a quite high plate count and yeast contamination, and we could see that on the microfiltration we reduced that to very low levels with the 0.8 and the 1.4, basically removing completely the yeast and reducing more than a log of 3 the plate count of the total plate count with the 1.4. So based on that, on the transmission and as well as the flux and the microbiology conditions, we saw that the 1.4 micromembrane is typically the best membrane for that, and as well as the 0.8 can be considered for improved microbiology plate counts as needed. From that permeate, we did another trial with ultrafiltration using 10 nanometer, 20 and 50 nanometer membranes, So basically, this is equivalent to 0.01, 0.02, and 0.05 microns to retain the proteins, and then let only the sugars and ions or salts to pass through the membrane. We did those trials with the feed with the permeate that we produced from the microfiltration before with the 1.4 micron. What we saw also is that we could not retain the proteins with the 0.05 micron. We had a transmission above of 100. The permeate with the 0.02 micromembrane, we still had a significant loss of proteins. And with the 10 nanometer micromembranes or 0.1 micron, we could increase, we could retain at least half of the proteins. So from that, we saw that for the liquid streams, the 10 nanometer micromembrane needs to have further investigations to adjust and check how to increase this transmission, or you can even use the traditional spiral wounded membranes to do this concentration of proteins. Anyhow, you can do the concentration of proteins after the liquid stream, after a microfiltration, because we can start to hold up back those proteins at the 0.01 micron membranes. Here are some pictures of the products obtained. So here you have what was feeded and what was the retentate from the microfiltration step. So you have a very clear product on the liquid that was feeded to the ultrafiltration, where the permeate is quite clear and the retentate is a little bit more darker for the ultrafiltration process. If we consider that traditional process starting from flowers and consider to change that process completely, getting out of the centrifuge and going to membranes, the process would be basically the same. At the start, we would be using the raw material and solubilizing that. Potentially, we could use less caustic or less enzymes to make this separation. We would go to a clarification process where we still have on the retentate side the solids, which are the fibers and insoluble materials, so non-protein materials. The microfiltration is going to produce a better liquefied protein stream or solubilized protein stream, because the microfiltration will be able to completely remove residual oil and fats. It's going to be able to remove oil burdens and spores, and it's going to be able to remove and retain all the suspended solids as the centrifuge. Potentially, after this clarification, we could do a fractionation just like we do in the milk process, to separate the smaller proteins like the globulins from the bigger proteins like the albumins, creating potentially two different products. And so on the retentate, you would have the globulins, the permeate, the albumins, and the ultrafiltration. And after you obtain the separations, you could purify even further the albumins by the usage of diafiltration. The good point on this is that the liquid phase that you are going to always have when you are concentrating those proteins, so you are removing the water that you added on the solubilization step, will have no proteins. Basically, it's just going to have the sugars and the salts that you have. So it's going to enable you to not have any losses of products or your target product, and also reduce the impact to the wastewater processes. After the both processes, you would be doing just as a normal processing of proteins, with having concentration by evaporation, spray drying, and then reach out to the final product as protein isolates. But in case the fractionation is a useful step for the given protein, you could have two products instead only one. Here are some results also for that total replacement of the centrifuge processes to membranes, using also the the P proteins as an example in a lab scale. So based on the first trials that we did for the liquid streams, for the side stream process, we selected the 1.4 and 0.8. We just tested the 0.8 and 1.4 micromembranes with very similar results. In this case, as the liquefied protein has different characteristics than so we have bigger protein particles, you have a more thicker liquid stream to be fed to the microfiltration. We observed that the 0.8 micron had a lot of a retention of protein, so lower transmission of proteins, and the 1.4 was able to transmit way better the proteins in the process. So then we repeated the test with the 1.4. We checked that also the transmission was sustainable at 85%. Microbiologically, the results were basically the same. The flux was quite lower, but the 1.4 had a way better transmission of those proteins. So this is one of the studies that we intend to do in the future, or even with anyone that is looking for changing their process from centrifuges to membranes, to consider the 1.4 micron, and inclusively, as Stephanie mentioned in her presentation, to use our Membralox gradient permeability membranes, which we could not do this in the lab scale, because those membranes can provide a higher transmission for proteins, which I will explain in a few why this happens. Downstream of this 1.4 micromembrane, we applied 20 nanometer membranes without this electric adjustment. As I explained to you guys on the traditional processes, you always adjust the pH of the clarified solution of proteins to precipitate the proteins. In this case here, we just got what we clarified with the membrane and passed it through our ultrafiltration processes with a 0.02 micron membrane, so the 20 nanometer membrane. We had very low transmission of those proteins, so we basically retained all the proteins on this process, and also by checking doing an electrophoresis qualitative analysis, we saw that everything that we were losing were below 20 kilodalton size, so potentially even going to the 10 nanometer membrane and adjust that, we could retrieve all the proteins. We did also a test for the fractionation perspective using a 100 nanometer membrane, and also we could see we saw in that case not so much higher transmission of proteins. So this means that the proteins in this case of the P proteins were above 100 nanometers, not so much below 100 nanometers, and we could retrieve and separate those proteins. So based on that, we could create two products from that. More studies are necessary, and even considering gradient permeability to check how to increase the separation of the membranes. But again, this confirmed it from the lab that we can work on processes replacing centrifuges to membranes. So here is some pictures of the product. As you can see, the microfiltration feed and permeates are way darker or have more intense full color. This is especially because this is way more proteins in those streams than it was on the tests that we did with the liquid side streams. And on the ultrafiltration from the feed, we got the retentate in the middle, and the permeate, which is a very slightly yellow color, very transparent, which is the permeate which has no proteins, and in the middle you have the retentate which was enriched with proteins. So moving forward, another way to produce proteins, which is also done for a long time, not for proteins specifically as today, or for proteins for food as is today. It's mainly done for producing enzymes or producing amino acids, especially for the amino acids, especially for some for human consumption, some for the majority for For animal feed production, it's a fermentation process where you get a microorganism, a biomass, so a source of sugars and potentially other materials that you want to change to become proteins, amino acids, or enzymes, or organic acids. Nowadays, it's very common to produce some ingredients from these fermentation processes, like some plant-based burgers today are produced, have some ingredients produced from fermentation, from fermentative processes. So we start with those raw materials. You do a fermentation using sterile air to ensure that you are not contaminating your microorganisms that you selected to make a certain function and produce a certain product. You are not contaminating them with wild other microorganisms like wild yeast, that they are going to compete for the biomass that you are doing there and avoid you to produce really your targeted product. After this fermentation, typically you need to do a clarification. Microfiltration is a solution, a great solution for these fermentation processes, because then the microfiltration is going to separate all the biomass and the microorganisms that made their function of producing the material. They stay on the retentate, and you just pass through the membrane the interested product or the proteins that you want to do. With this permeate, you always can go after with the permeate, which is going to be rich with proteins. You always can go to an ultrafiltration step and use that filtration to wash out sugars. Then you go to typically the evaporation and spray drying and protein isolate processes. And on the retentate side, you are producing a biomass, which can be at the end of the day used for animal feed, because you have to, as you are doing a membrane process, you don't have to use any type of filter aid to make the clarification of your fermentation broth, which is the other traditional way to do it with hot air vacuum filters or pressure leaf filters. So just to talk a little bit about the fermentation, it's very important to consider the air filtration. You typically on these fermenters, you have a dedicated compressor, a dedicated line to feed air to your fermenter. And the filtration, especially the sterile filtration of those that air, is highly important to avoid the contamination of your reactor and contaminating your microorganism with other microorganisms that are going to compete the filtration. Depending on the application, is also important that you have the exhaust vent filtered. So when you are whatever gases you are producing from the fermentation, you have to let them go to out, even if you are pressurizing a little bit your fermenter. In some cases, it's important that you have a sterilization of this exhaust vent air also, to avoid contamination of the environment or to lose any sort of protein. Typically, on those applications, you are targeting to have very high reductions of the contamination above log 10, log 7. And those cartridges that are claimed, on our case, that are claimed with that they are sterilizing filters, they are always bacterially challenged with B. diminuta, and they are produce this above 10x to 7 counts reduction of the membrane. So basically, from every 10 billion cells that goes to the membrane, just one cell can pass. So comparing membrane filtration with the direct flow filtration, with the traditional DE or Kieselguhr filtration, in the direct filtration, you have your feed going through the filter, where you have to produce a cake with filter aids to obtain your filtrate, and in the cross flow, you are recirculating your product with your biomass without the usage of any filtrate in a tangential position of the membrane and creating the filtrate on the permeate side. So the major advantages of moving to a cross-flow filtration instead doing directly filtration is that you can make a fully automated process, you can make a fully continuous process. You don't have to use any filtrates. It's easier to make the cleaning on the membrane. You really have a physical barrier to retain the materials that you are looking for. It's not the interaction of the cake and the filter to do it. And especially with ceramics, we have a very long service life filters. So talking a little bit about microfiltration. Microfiltration has the operations and both the membranes and the operation conditions are going to impact to the filtration performance. Here on this picture, you can see the cut and magnified in the lab cut of our membranes, where you see in the bottom part the structure of our membrane, and in the top part really the membrane in ceramics, which can be 0.8 micron, 1.4 micron. If I'm not wrong, this one is a 0.2 micron example. So you can see that on the feed flow, with the flow direction of the cross flow, you have those orange and green particles, where the orange particles are intended to show what are macromolecules, cells, oil droplets, and the greens are really the dissolved molecules. And then you're also always going to have water or a solvent if it's the case, and the ions that are going to pass through the membrane together with the dissolved molecules, and the macromolecules or oil droplets or cells are going to be retained. It's very critical in microfiltration applications. What you are looking to do is you're really just looking to do a clarification, so really retain solids and transfer the dissolved solids, or if you're targeting to do a fractionation, where you want to retain some of the larger molecules and transfer the smaller molecules. And to achieve that, you have to play always with the cross-flow velocity and transmembrane pressure that you are operating. And for the microfiltration for fractionation, the major challenge is the polarization layer that you create over the membrane. Every cross-flow process is going to create a layer on the side of the membrane. If you think that this orange part here is the membrane itself, and the white side here, you have the tangential flow rate operating. As much as you are near to the membrane, and you have to think that this is a really few millimeters or few microns of the cut of the membrane, you create a layer of the materials that you are retaining with the membrane that can create another layer of filtration. And this can create a lot of challenges for you to pass those smaller molecules and just retain the larger molecules that you want. So the process and the membrane selection in this step, it's very important, especially with some lab trials, to adjust really the condition of TMP that you have to work and the membrane that you are working, to ensure that you are not creating any transmission or retention, or you are trying to reduce this as to a minimal point. So this is where it's important to any membrane process to have a process know-how, the process design capability to work in these processes, and also it's where our GP membranes can play around, because the gradient permeability can help to reduce the effect of this boundary layer. Now, talking a little bit about the GP membranes, if we get our standard Membralox membranes, or in this case, is the same behavior for any membranes, being ceramics, being hollow fibers, being spirals, or being flat sheet membranes. Through this retentate side, or this feed flow that you have, you're always going to have a high flow rate passing through the channel of the membrane. So it's creating a pressure drop from the beginning of the membrane to the end of the membrane, which makes the flux profile to be very high in the beginning of the membrane and very low in the end of the membrane. And if it's a standard application that has no transmission or retention problem for your process, This makes no difference. In the end of the day, you are interested just in the flux to be there, and the flux is going to be the average of this difference here. But if you have some sort of challenge with transmission, as you start to have too high flux profile here, you have the tendency of having a lower transmission in this point than in the end point. So you are passing a lot of water and not your product of interest, and in the end of just in the end where you have a very low flow, you are passing your product. So you start to lose your product into the retentate. When you have the GP membrane-locks membranes, as we change the permeability of the support layer, we are able to make this flux profile to be the same all over the membrane. And this helps for you to create the same transmission all over the membrane, increasing your final yield of production of your interest product. In ultrafiltration, which is the step that you really want to retain material, in addition to the pore size of the membrane that you want to retain, you have to think a little bit about the performance and the process that you are using. You have to think about the transmembrane pressure that you are operating, and target to have this to find the critical TMP, or the point of the TMP that you are working, that you start to drop flux, because this is the point that you start to retain more materials that are smaller than the pore size of the membrane. So this is where you start to have the retention rates on the ultrafiltration membranes, where you have really the common statement that ultrafiltration membrane has a 10,000 kilodaltons molecular weight cutoff. The other membrane has 5,000 daltons molecular weight cutoff. So this is not only the membrane itself, but also is the TMP that you are operating that membrane. So this is a very important point when you are investigating ultrafiltration. Sometimes membranes with a higher cutoff can deliver the same result just because the critical TMP they are operating. Here I'm going to show just a side stream case study from plant proteins. So you have here the product before the production, which is very foamy and very full of suspended solid materials. You have here the ceramic system with membrane locks. This case has more than 1,000 square meters area of filtration. We have in this process a retention of 99.5 of the suspended solids. We have a reduction of the bioburden or the contamination of the material above log 3. We have less than 5% of the proteins being retained, and the sugar and salts, they all pass through the membrane. And this is the product on the permeate side that is obtained from here, which is a protein broth. As you can see, it's quite a clear product, which is just enriched with proteins going to the next steps. So one of the takeaways we want from here is that the membrane processes allows you to recover and add value from the side streams, especially turning waste into valuable products. You can come also from the acidified proteins, which is a traditional way, do additional processes to produce more products and separate also the products that you have by using the combinations of microfiltration and ultrafiltration. And especially as we are doing this process with membranes, we can do those processes at lower temperatures without chemicals and filter aids, which is a major benefit. And also one of the benefits of the membrane process is the removal of bioburden and spores. So thank you for your time. I don't know if we have time for questions or if this is planned on the presentation. I will stop sharing here.
Thank you, Rodrigo, and thank you to all our speakers today. We will shortly move into the Q&A section, because we have a few open questions, although a lot of our questions have been answered by our experts. And thank you again for giving your time first to the participants, as well as everyone from Pall Corporation. And I'm just gonna put in the link to contact Paul after the webinar in the chat. So yeah. And I think we have a few open questions. We can just quickly go and answer them. And please, if you have any other questions at this point, do put them in the chat, and our experts and myself can answer them. So the first question is, can you explain a bit more about filtration monitoring tools? And I guess the best person to answer this would be either Prashant or Rodrigo. So whoever one of you wants to go and answer this question.
Yeah, if you wanna go, Prashant, to talk a little bit about our equipments, but just as a general process, the major filtration monitoring processes is the controller of the system, and always controlling pressure and filtration and turbidity, but also to understand the lifetime of sterile filters, especially which are the ones that needs more monitoring for the filters itself. I would give to Prashant to answer. Prashant?
Yes, I think I agree with you. And downstream monitoring, and also particularly if you are looking for the product, if you want to bring the product into a particular segment, like where you need more stringent laws need to be followed in terms of having the data of microbiological validated membranes, particularly the food contact compliance, and also the product with the integrity testing possibilities, wherein you every batch of process use, if you can have the data produced after the filtration being used, that can all support.
Great. So we can move on to the next question. How can companies like Paul, along with producers and manufacturers, band together to increase the availability of raw material? Would this require reduction in ag exports? So, at GFI India, we've thought about this question a lot in the last 6 to 8 months to, ensure that the momentum in the market is continuing. And I can answer this question essentially, talking about specifically, we definitely require, companies, but also, like different companies across the value chain, but also, a lot of the universities in the Indian ecosystem who are doing work on specifically raw material availability to come together and to, work with people on the farm gate and people who are producers as well as traders of, indigenous crops such as pulses to really make our raw materials viable. A couple of things that many end product manufacturers have told us are that the protein content of some of the crops in India, it's not as high as some of the imported raw materials, and secondly, the batch to batch variability is really kind of hindering them using Indian sources, because a lot of the Indian manufacturers would like to not essentially rely on imported raw materials that would help them bring their costs down as well and pass it on to the end consumer. And secondly, your question about would this require reduction in ag exports? I wouldn't think so, because again, for specifically, like in fact, this could potentially help us increase exports of value added products, but also looking at some of the specific volumes that right now, especially looking at plant-based meat, eggs, and dairy applications, the volumes are not nearly as large per se. So I don't think it would have an effect on like require reduction in our ag exports. In fact, it could be a way that some of our exporters already could produce more value-added products in the near term. So yeah, that would be my answer to the question. And secondly, I think we have one last question about is there a pilot plant facility in India where protein concentration and isolation can be tested? So Prashant, I think you're already wanting to answer this question live. So from Paul's perspective, I'd love to give it up to you.
Yeah, I think there are different solutions what Paul can provide to our customers here in India. We have our systems available for lab scale. Customer can come down to our lab to have a quick slip trial at a lab scale. If they are working on a new molecules, if they have working at a certain scale, like let's say 5 to 10 liter or 100 liters, and they want to do the trials at a production scale in their facility, and Paul can build a system customizing to them, or use an existing piloting system to be there at their production facility and do kind of a trials for both micro filtration as well as the ultra filtration to help out customers. So on the filtration optimization steps.
And Prashant, as a follow-up, where would this facility be located?
We have a system available readily in Bangalore. We have currently the technical lab in Bangalore, and in future, from next quarter or maybe let's say next 2 quarters, it is also available in Pune. So both Pune and Bangalore, I could say yes.
Understood. Thanks, Prashant. Also, if you are interested in knowing more about, kind of like specifically, places in India where we can test protein isolation and concentration, do reach out to me, and I'm providing my email ID in the chat. So yeah, I think those were all our questions.